faculty. Hello, bonjour, good morning, good afternoon, good day to all of you, wherever you are. I hope you had a good break if you were with us this morning. Welcome back to all the viewers that were with us earlier today or this week. We are still at SNT 2021, and to start this afternoon in Vienna, we have the privilege to have Professor Guy Brasser to give us a highlight talk about the atmosphere and its dynamic. And so I would like to first thank Professor Guy Brasser for joining us and accepting the invitation. It's a real privilege to have you with us today. And after a very interesting talk 2 years ago by Michel Jean from the World Meteorological Organization and from Meteo Canada, we have a new highlight talk with a new perspective today with Guy Brasser, who was quite an interesting career, going from different places, in particular the NCAR in Boulder, Colorado, and now at the Max Planck Institute in Germany, in Hamburg, where also in Hamburg he founded the Climate Service Center over 10 years ago. So a lot of experience to share with us today and to be talking about progress and challenges in atmospheric sciences. And I don't want to take too much time, so I will just ask Professor Brasser to jump in and deliver us his highlight for the day.
Well, thank you very much. Thank you very much, Pierrick, for your kind introduction and also for inviting me to talk about the atmosphere, which of course is a very wide topic. And so what I'm going to do, I'm going first of all to share my screen and to move into the PowerPoint here, which is appearing, and indicate to you that essentially what I will be doing is to talk about predictability of the evolution of the Earth system, of course, in particular of the atmosphere. And so what I would like to do, when we talk about the atmosphere, we of course talk about weather, about climate, about air quality. But what I would like to do is to really provide an historical perspective that has shown the long evolution of our understanding of the atmosphere, and then finish my presentation by highlighting a number of important challenges that we have to deal with. No, I'm trying to get my... Okay, so the Earth is a complex system. And a complex system has a lot of multi-scale processes that interact with each other. We have to look, when we deal with the atmosphere, to basically a component of a system that includes, of course, the ocean, the land, and a lot of transfer of energy and momentum between those different components. And of course, today, NASA, for example, but I should say other space agencies also, like the European Space Agency or the Japanese Space Agency, see the Earth really as a complex system that needs to be investigated by the most advanced technologies. And of course, satellites provide a lot of information on the different components of the Earth system. At the same time, Earth system scientists, climate scientists have been developing complex atmospheric or Earth system models that deals with the different components, the atmospheric circulation, which we will discuss a little bit, but also the chemistry that influence very much the Earth system. Then, of course, the ocean, its circulation, the biogeochemistry, the sea ice component. On land, we have to deal with, of course, land physics, land hydrology, plant ecology, and then, of course, talk about continental ice sheet that are affecting all that. And these mathematical models that are now a very centerpiece of the research, well, they strip the complexity of a system by identifying the essential driving variable and describing the evolution of these variables with equations that represent the physical law, but also sometimes provide empirical knowledge. So the connection between models and observation at different scales, including surface observations, for example, are very, very important. Those models can be, of course, of different nature. They can be following the first principle, which means the physical law. They can emphasize empirical information, as I mentioned. They can be analytic or numeric. They can be deterministic or stochastic. They can be continuous, discrete, etc., etc. So what I would like to do in this presentation is really to go through the historical evolution of knowledge. And I'll talk about the predictability of the weather. I'll talk about the predictability of climate. I'll talk about the predictability of air quality before moving to challenges for the future. So we're going to start with the predictability of the weather. And the key things to understand here is that predicting the weather is really an initial condition problem. We need to know the situation now to derive what the situation will be in the future. And of course, we go back to Newton's law that has, of course, indicated that the change in velocity, the acceleration, is proportional to all kinds of forces that act on the body. Here, let's say, the atmosphere. And of course, this has translated into the approach that the Norwegian School of Meteorology developed very strongly, with Bregnes as the key figure, that said that basically, if we have a sufficiently accurate knowledge of the state of the atmosphere at the initial times, and a sufficiently accurate knowledge of the law of physics, according to which one state of the atmosphere develops from another, we could, in principle, predict weather. And so, like 100 years ago, following those principles, Bregnes suggested that weather forecast is a deterministic problem. It can be solved by resolving the fluid dynamics equation. And the first attempt to do that using numerical solution to those complex equations was done by Richardson, who during World War I, he was an ambulance driver and he had times to do a little bit on the side, things that he liked to do. And so he tried to solve the weather equation, but he did it by hand at that time. He covered Europe, in particular the UK, with a grid, the first grid, pretty coarse. He had some initial value at some of the points that are cited, the observation station. And he started to solve the equation, but realized that it was a tremendous enterprise, so that he said, well, if we really want to do it in an empirical way, in an operational way, we need to develop a numerical factory to perform in parallel all these operations. And so he saw things being like in a theater with a lot of people writing, solving part of the system, and basically defining here what I could call a human computer. In fact, the story is that he failed in his first attempt because of reasons that are well known: instability in the system, poorly defined initial condition, etc. And it's really later on, with the development of the first computers that were not humans, that were electronic, that integrator of the equation became possible. The first computer was the ENIAC computer. And in fact, at that time, a simplified version of the equation, which called the quasi-geostrophic approximation of the hydrostatic equation. So basically, eliminating a number of waves like acoustic waves, gravity waves, but retaining the large scale wave, and were kind of at the basis of this model. And Giulio Ciani, who was a professor at MIT, worked with a famous mathematician von Neumann to really try to solve the equations. And you see here the computer of the time. It's always nice to see these old pictures. So at that time, it was really believed that weather was a deterministic problem that could be done relatively easily for a long period of time. But then we have to go back to Henri Poincaré, who basically showed that when the solution depends very much on the initial condition, complexity enters in the game, the system becomes chaotic, and the atmosphere is a chaotic system, so that predictability is limited because of the small error in the initial condition, and they are really rapidly growing. And of course, there are approximations in the model that also introduce difficulty. And you will see in a minute how the meteorologists try to go around this. Of course, another example was provided later by Lorentz, who was solving these simple equations, but they are nonlinear. And when he did that, he saw that two solutions with two slightly different initial conditions provided solutions that were relatively parallel, very close to each other at the beginning of the integration. But then suddenly they started to diverge. As you see here on the right panel, the blue solution after a certain time becomes very different from the red solution, and there is obvious difference, so that the length of the prediction is really limited. And that because of the uncertainty in the initial condition and their growth with time, today people are providing ensemble forecasts, starting the forecast with slightly different initial condition and looking at different possible realization of the forecast, taking then the probability of occurrence between them. And that's why today you have usually a forecast that is based on a probability of certain processes occurring, and that's coming from the different realization of the different models that are used. So there are limits of predictability, and I'm listing here quickly the sources of the predictability. First of all, you see here large-scale forcing, teleconnection between a geographical region, interaction between the atmosphere, land, vegetation, and ocean. But they also source of unpredictability, and that's the instability injecting chaotic noise at small scale, upscale propagation of energy from scale interaction, error associated with the numerics of the model, error in the parameterization, and insufficient number of observations. And so a number of things have been done to improve the skills, the predictive skills in the model. It's improving the representation of those small scale processes, doing the ensemble, as I mentioned, and introducing objective analysis technique to include information from observations, essentially, better treating observation, in particular with what we call assimilations. And I'm not going to talk about that very long, but the assimilation in particular, for those who know the techniques, the 4D VAR assimilation technique has improved greatly the weather forecast that we have. And you see here, for example, this is for ECMWF. If you look at the blue curve, this is a 3-day prediction. And you see that basically the forecast has improved very much over time, essentially due to the improvement of the assimilation processes, but also the fact that we have more observation. And now we can really reproduce basically the situation pretty well. You see on the right here a forecast by ECMWF, and it's compared with what then was observed by Meteosat. And you see that basically the forecast is pretty good compared to what has been then observed in the subsequent hours following the forecast. So far for the weather. Let's move now to another aspect of atmosphere-related science, that is the predictability of climate. And here it's not an initial condition question or problem, but it's really a boundary condition problem, forcing of boundary conditions. And so if you think about people were trying to predict climate change since Fourier discovered the greenhouse effect in 1824, and Arrhenius, the Swedish Nobel Prize in 1896, tried to do a number of calculations, a bit of a back of an envelope calculation, but he predicted that a doubling of CO2, which in fact he had hoped to avoid the cold weather of the north, and in particular the possible coming back of a glacial period. He had said, well, if you double the amount of CO2 in the atmosphere, you will increase the mean temperature by 5 degrees, which, by the way, is not that far away from what the current models are predicting. But that was a very back of an envelope calculation. And of course, it are people like Norman Phillips and then other American scientists to a large extent who have been developing the first global atmospheric general circulation models that were then coupled to ocean models to try to see how climate would evolve. And so let's look a little bit at the long-term climate projection. And to do that, we work today with basically interactive model that includes an atmosphere, an ocean, the land surface, and include different ingredients, the dynamics, the chemistry, and then you try to look at all the interaction that exists between those different components of the Earth system. So the question is, can we predict climate? So the real question is weather is not predictable beyond 2 weeks, for example, as we mentioned a bit earlier. Can we then predict future climate? The answer is really no. We cannot predict the future state of the atmosphere on Decadal to century timescale, but we can perform an ensemble of simulation with many realizations, just a bit like in the weather prediction, and derive not exactly what's going to happen, but derive the change in the probability distribution of climate states. In other words, we can calculate not the temperature in the future, but the mean temperature in the future, maybe the variance of around these means that we should expect. So rather than predicting, we say that we can project the evolution of statistical moments, such as the mean and the variance of climate variables, including temperature, but also others, in response to greenhouse gas emissions. And this is here an example. You see a number of possible scenarios of emissions on the left side here. You see different scenarios. One here is basically they have names, RCP 8.5. It's basically business as usual when you compare the past evolution. But then you can go to the other extreme, which is RCP 2.6, where we really decrease the emissions of CO2 so much that we do not let the temperature go over 2 degrees. That's what one is trying to do. And then you have intermediate scenarios that are here. These are the scenario on the emissions. These are here the scenario on the concentration that results from these emissions. And you can see we are now in 2020-22. We are getting close to 420 ppm, when in fact in the pre-industrial time we were at 280. So the level of CO2 has been increasing. And of course, depending on the emissions, different evolution of the atmospheric concentration will be changing. Now, let's take here 2 scenarios, the business as usual, RCP 8.5, and then the minimum one, a smaller one, RCP 4.5. And you see here the calculated mean temperature. And of course, you see a lot of noise around that. That's basically due to the fact that we're using different models. They provide different solutions, but each model had its own initial condition changing so that you have the internal variability of the atmosphere that plays a big role, and that creates this noise around the moment, which is here the mean value. And you can see that if we take business as usual, 8.5 in 2100, we are very close to 9 degrees Fahrenheit, so about 4.5 degrees centigrade increase, but with a large uncertainty. And you see here the uncertainty associated with the different scenarios. This is now back in Celsius after Fahrenheit divergence. You see here for the two scenarios, this is the minimum scenario where we try to keep the temperature below 2 degrees, consistently with the Paris Agreement. This is the business as usual scenario. And you see here the temperature, the distribution of the temperature change. Well, here we're close to 2 degrees, but here we are much more in the red, going up to 7 degrees and perhaps 9 degrees increase in the polar region, which of course will have a major impact on the state of the ice and of the regions. So that's so far for weather and climate. So let's go now to the predictability of air quality. Now, atmospheric chemistry is, of course, a nonlinear issue, but it's not so much associated with chaos. The chaos that affects air pollution or air chemistry is really provided by the chaos of the dynamics of the atmosphere, and therefore the transport of the chemical species that is associated. But still, the air pollution issue is a major issue. You know that probably 7 million people die prematurely each year from indoor and outdoor air pollution, probably about 3 to 4 million from outdoor pollution. And this is here a picture of what happens in Delhi on one of these days. I could show you many of these pictures taken other places. But we would like to also predict, or at least understand, use models to understand and predict how the air quality and the chemistry of the atmosphere is changing. And these models are pretty complicated also because first they have to calculate pretty well the dynamics of the atmosphere, which is very important to understand the transport of chemical species. And you have to do that at different scales, not just on the global scale, but also at small scales, which affect very much chemicals. For example, the transport in the boundary layer, say in an urban area, is very, very difficult to capture in a model that has a resolution maybe of 50 kilometer or 100 kilometer, a spatial resolution of that nature. So these kind of models include, first of all, emissions, and emissions can come from agriculture, from the vegetation, from the urban areas, from traffic, from industry, from residential area, from airplanes, from biomass burning. So all these primary emissions enter in the atmosphere and release a number of species that are listed here, not only CO2, but black carbon, methane, volatile organic compound, nitrogen oxide, SO2, carbon monoxide, ammonia. Agriculture, for example, released a lot of ammonia. And then those species are being transformed by nonlinear chemical reactions, number one, and then produce what we call secondary pollutant, like ozone, for example, or many particles, matter here that you see. Now, these species are affected, of course, by the meteorology, by transport, by the clouds, by the rain. And so finally, you have a very different complex. So you need to validate your model also by observation, for example, ground measurements, satellite observation, and then you have three-dimensional models here. Now, one of the important aspects is the transport, and I don't want to discuss that too much in detail, but the ARISE infrastructure project from the European Union has been doing an excellent job in looking at the transport not only near the surface, but also in the upper atmosphere, and showing, for example, the role of planetary waves, large-scale waves that occur in the atmosphere, but also gravity waves, and finally the transport from the tropical region to the polar region. And then looking at sources of a number of waves that occur in the atmosphere. So that's an example of how basically the people who do analysis of observation can help integrating this kind of observation in complex models. Now, the models do not only include the dynamics, the transport, but also the chemistry. And so the chemistry is very complicated, in fact, and very nonlinear, as I mentioned. So you can see here at the bottom different sources of emissions of chemicals that release, for example, volatile organic compounds, nitrogen oxide, sulfur dioxide, ammonia, as I mentioned. And then there are a lot of reactions occurring here, leading to those secondary species, like ozone, for example. Ozone is formed from essentially the presence of nitrogen oxide and the VOCs, both produced at the surface, so strong anthropogenic component, and the action of ultraviolet solar radiation. On the other hand, the particles that you have to deal here, they can be produced by direct emission, so there's a primary aerosol, but the rest, sulfate, nitrate, and secondary organic compound, are secondary species produced by a number of complex chemical pathway that occur here in the region. And so what I would like to do is to show you basically a simulation of a gigantic and unplanned experiment that took place very recently, 2020, and still now. So what is it? It is essentially the response of societies to the COVID situation. And so basically emissions of primary pollutants and greenhouse gases were severely reduced during several months of COVID because of the reduction in economic activity. It started in China, where during the January-February lockdown in China, the emissions were pretty strongly reduced. And then it went on in the rest of the world with probably, if we look at the first wave, we don't know how many waves we're going to have, so let's look at the first wave. Well, it was more like in March, April that the effect was occurring. And so the question was, okay, primary species were reduced. That was expected. But what happened to secondary species? The one that I mentioned a bit earlier, in particular, we're going to look at ozone, which is, it's formed by nitrogen oxide and VOC. Nitrogen oxide is produced by combustion. That means including cars and traffic and so on. And so there's been a strong reduction in NOx. VOC are produced essentially by industrial activity and also by cars and so on. And so there was also a reduction in the VOC. What happened to, for example, ozone? Now, why do we do that? Because this worldwide chemistry experiment mimics, in fact, the attempt that we have to clean up the atmosphere. We want a reduction in the pollutant. And so it gives us basically a little bit of information about how to conduct really policy that would lead to better air quality. So we can go, first of all, to satellites. And the satellites are measuring, in particular, nitrogen oxide. So the top here is a view from space of nitrogen oxide in 2020. So this is during essentially the COVID. The lower level is a year before, no COVID. And so basically, it's a bit difficult to analyze because there was also in China the spring festival, the New Year, the lunar New Year, which is not taking place at the same time. But if you look, this is before the lockdown was declared on the 23rd of January 2020. So you see the results before the lockdown were not too different. Here we had the lockdown, which is shown here by this little thing. And we see that there was a reduction, also probably caused by the New Year, the Chinese New Year, but here the New Year was over. And in fact, you can derive some reduction. So you can see the same thing essentially from ground stations, because satellite show you basically the total amount in a column below the satellite, but what happens really at the ground. So if we look at nitrogen oxide, which is in the middle here, we see what happened before the lockdown in 2020. And you see there are quite a few red points and yellow points. Then if we look after the lockdown, the same year, we see that the points have become blue, which are much lower. So there's been a 40% reduction in the level of nitrogen oxide. We see the same thing with the particles. See that the red here, and then after the lockdown, the value are more like in the blue, which is a strong reduction. Let's see what happens to ozone. Ozone is not emitted, it is formed in the atmosphere. And so what do we see in China? We see here the value before the lockdown, and after the lockdown, ozone has increased. And so this is a bit surprising, because you clean up the atmosphere, and one of your pollutants, namely ozone, which is bad for your health, etc., is in fact increasing. So we try to simulate that with a model to try to understand. And so there's been basically some estimates of how the emission have been changing due to the lockdown. And you see, for example, road transportation, probably 60% reduction in Europe. You see here in China, it happens before. By the way, there's been an increase in the emission due to residential activity, because everybody stayed home. It was winter or spring, heating went more on. And you see also here basically an estimate of the change in aviation. We'll come back to that in a second. So you can apply that to your model and change your emissions accordingly, both for different sectors and for different species. And so you can then calculate the change in the concentration. So we're going to start with the nitrogen oxide, really emitted. So basically, we expect the concentration to follow very much the emissions. And so on the left, you see the situation for February. On the right, you see the situation for April. So in February, we see here a reduction, maybe 30-40% of the nitrogen oxide occurring essentially in China, where the pandemic had really started. But just 2 months later, the whole world had been adjusting to that. China was over. It was over. The pandemic was to a large extent over. So the activity started again. But in other parts of the world, in Europe, in North America, in South America, people were confining and the emissions were reduced. So what happens then to ozone? Because remember, ozone is produced by the action of NOx, nitrogen oxide, and the VOC in the presence of UV radiation. So that's what you saw here. Not much happened in the rest of the world, except China. We're close to zero in February. And then in April, we see essentially in the green, a reduction in ozone with some slight difference, in particular in urban area. But what is interesting to see is that in China, the southern part of China saw also a decrease in ozone, but the northern part of China saw an increase in ozone, just as we had seen in the stations. And in fact, this can be explained by essentially the photochemistry. The photochemistry is nonlinear. And so if you are in a not too polluted region, ozone is built up with NOx, more ozone. If you are in a very polluted area, like northern China, the region of Beijing, what you see is that the photochemical environment is changing completely. There is more NOx than ozone. And so a reduction, NOx titrate ozone, destroy the ozone. And so a cleanup of the atmosphere by reducing essentially the emissions of nitrogen oxide does not reduce ozone, as it does in most parts of the world, but it increases ozone. And we know that this is happening in northern China. I mean, we saw it during the COVID experiment, but we know it's also occurring in very polluted cities, Delhi or Los Angeles or Mexico, etc. We see those kind of reaction, and in particular, in the cities, very often, we have more ozone in the weekend because there is less traffic and there is reduction of NOx, but we have more ozone and even sometimes more particles than otherwise. So that's the surface. So let's see now what happened during COVID in the atmosphere itself, not just at the surface, but also as a function of altitude. And so you see here essentially between January and December for many different years between 2000 and 2019 and 2020, the amount of ozone that you have at 6-kilometer altitude. So in the free troposphere, and you see it as an anomaly with a mean of 0%. And you see the different years, of course, have different value. But what was interesting here is that in 2020, we had almost up to 10% reduction in ozone, not just at the surface, but also in the upper atmosphere, in the free, well, at 6-kilometer altitude. And so what are the potential forcing mechanisms that exist? Well, potential forcing mechanism in the free troposphere is, of course, the reduction in the surface emission at the surface, as we discussed when we looked at the response of ozone and at the surface. But there was also the reduction in aircraft emission during the pandemic, which has a large impact in the upper atmosphere. And then we had the influence of the exceptionally large reduction in the Arctic ozone in the lower stratosphere during March and April. So we had not Arctic, we had an Arctic, that's right, we had an Arctic ozone hole that was associated in 2020 with a real strange meteorology that was occurring. So let me show you this quickly. You see here the total daily flights for different years from 2016 to 2020. And indeed, in 2020, we had a severe reduction in air operation. But we also had this Arctic ozone hole that occurred. We haven't been talking much about it, but ozone was very low in March and April 2020. And it's in the stratosphere, but it could influence the lower atmosphere or the troposphere, maybe as down as 20-kilometer altitude. So you see here in red the data, as I showed you earlier, at 6-kilometer altitude between January and December, and you see that there was a reduction here. The blue curve is our model that represents to a certain extent what has been seen. This is ECMWF model that has not taken into account the reduction in the emissions, but has taken into account the effect of the Arctic ozone hole. So clearly the Arctic ozone hole was contributing to the observed anomaly in addition to the COVID-related aspect. And if we look now here at the vertical changes occurring between the surface and about 10-kilometer altitude, we see that the observation showed up to 15% anomaly at about, let's say, 8-9-kilometer altitude. The model shows the same thing here, and then 5 to 10% reduction ozone at the surface. And of course, what happens in the upper atmosphere is it's not COVID related, strongly associated with the meteorology and the appearance of an ozone hole. If you just look in April, this was the average between April and June. But if you look just in April, you had like 25% anomaly in ozone, to a large extent associated with the ozone hole in the Arctic, but also lower down associated to, well, the airplanes contributed. The lack of NOx emission by airplane was affecting ozone. and the surface emissions being reduced due to the COVID. So all that contributed to what we saw. So I just wanted to show you an example here of the kind of thing that we can do now with models and how we have improved our capability of predicting essentially the state of the atmosphere, both from the dynamical and the chemical regions. I'd like to finish with a few challenges that the community, the meteorological and atmospheric science community, has to face in the future. I talked to you about the long-term climate change, but we're also very interested in the seasonal to decadal climate predictions. Can we predict climate change? I mean, we know that what we can do with the weather. We know that long-term predictions are not possible, and that therefore we talk about projection of what could happen. What about this intermediate scale between weather and climate? Let's say the seasonal, and we can go to decadal prediction. So what are the sources of predictability? It's a very hard problem to solve. There are sources of predictability. First of all, external forcing, just like for the long term, has an impact. Greenhouse gas emissions, aerosols, changes in solar radiation. Solar, the sun moves with an 11-year cycle. That has an impact on decadal aspect. Volcanic eruptions, well, we cannot predict them, so we call them the wild card. But there are also some sources of predictability associated with the internal system, with the natural variability in the system. There are, for example, what we call slowly evolving mode of variability of the ocean. The ocean reacts much slower than the atmosphere. And so if we see what happens in the ocean, we might have some, it might have some impact on the way the atmosphere will react on the same time scale as the time scale of the ocean. So that gives us some years maybe of predictability. There are, of course, long-term persistence of certain physical or biogeochemical processes that we can take into account. And then, of course, if you want to do a prediction for season to decade, you have to know not only the initial state of the atmosphere, but the initial state of the different component of the Earth system, the ocean, the land in particular, and they must be very, very well provided to the model. I mentioned those basically patterns of variability on decadal time scale. And so El Nino is one of them, the Pacific decadal variability, the North Atlantic oscillation, the Sun hemisphere annular mode, and Atlantic multi-decadal oscillation. So these oscillations in the ocean, which are relatively slow, maybe several years time scale, can give us some hints about how the atmosphere will be responding. And here's, for example, showing you the evolution of the North Atlantic oscillation, which has a big impact on the way the weather occurs. And so by trying to capture that in models, we might make progress on these seasonal to decadal predictions. Another aspect where progress is expected are very high resolution representation of the atmospheric physics in Earth system model. And I'm going to show you here a kind of a movie to show you what very high resolution models can do these days in terms of representing, for example, the formation and the evolution of the clouds. Now, this is not an observation. This is not a view from satellite. This is really what a model is doing. And you can see that basically now we have the capability of really reproducing relatively small scale processes with, like meters of resolution. That requires, of course, large computer capability, but also it is where basically a better understanding of the physics will be operating. Another challenging issue is to use what a lot of people are doing now in different disciplines, but it's use artificial intelligence for improving prediction. I'm not going to talk too much about this, but the field of machine learning enables probably breakthroughs, both in detection and analysis of complex relationships that exist, also patterns that exist in large multivariate data sets. And so we think that by adding machine learning to the modeling, the traditional modeling activity, we will enhance basically our predictability. We will, first of all, enhance the Earth observation data set, accounting for the different kind of covariation that exist in the system between different variables, and they all related. We want to basically do a better job in defining the parametrization, and in particular the subgrid scale aspect that we cannot treat in traditional models, because the models today have a finite resolution, and so small processes are not captured by these models. But that should allow us to better understand clouds, land surface processes, etc., which has been a bit a problem in climate modeling. And you see here different types of different variables that are observed from satellite, and by combining them by artificial intelligence, we expect probably to go beyond what the traditional model are able to do. Finally, I think I have two more challenges here. One is what we call climate intervention, or you could call it geoengineering. But of course, when you are looking at climate issue, our effort is, of course, to reduce emissions, also perhaps to adapt to some of the climate impact that we are expecting. That's the first line of defense, but we have to find other options too to reduce the warming in case the reduction in emission is not reaching the level we expect to stay, for example, below 2-degree warming. So solar geoengineering to cool the Earth by adding small particles, reflective particles in the upper atmosphere, aerosols we call them, or by increasing the reflective cloud cover in the lower atmosphere, or by thinning high altitude clouds that can absorb heat. These are strategies that are put on the table. They're dangerous politically. We can talk about it, but because nobody knows exactly who would control these kind of actions, and there is no mechanism today to stop a country, for example, to start developing geoengineering techniques that could improve the situation in one country, but could worsen it in other countries, for example. So it becomes a high social and political problem. From the scientific point of view, we think that strategies like this have the potential to reduce the global temperature, but it could also introduce some unknown negative consequences. And so we feel that studying this is important. Implementing it is another issue. And even if we did that, and at the same time CO2 would continue to increase, it would not avoid, for example, the impact of carbon deposition in the ocean, and in particular, touching the acidity of the ocean, for example. So here is just to show you the kind of thing that would be happening here by different approaches, changing the surface albedo, increasing the reflectivity of clouds, increasing the amount of aerosol in the atmosphere, and perhaps even putting mirrors in space to try to account for, basically increase the reflectivity of solar radiation. Finally, we said a word about air quality and chemistry. There are now, of course, currently people are trying to develop models that are supposed to predict air quality, but also attribute air pollution to sources so that we can address this and reduce the sources. Basically, people have been working with global prediction models, very expensive with low resolution, typically 100-kilometer resolution, so you don't see much what happens in urban area or in very polluted regions. And so regional models with higher resolution here, 12-kilometer, have been developed, but these models are not really accounting for the interactions between scales. And so one of the directions that the atmospheric chemistry is taking now is really to work with basically grids that are unstructured, and they treat the whole Earth, but they zoom on the regions of interest. And you see here two examples that exist. Let me conclude, not very long, because I have been going through a long history, but what I would like to highlight here is that it is high time for the different communities, the dynamical meteorologists, the atmospheric chemists, for example, but also the climate scientists, the biologists, and later on, of course, even social scientists, environmental engineers, etc., to work together towards having a system that basically improve our predictive capability by incorporating and integrating weather, climate, air composition. And you see here essentially a design of that with, first of all, the development of couple environmental models at different time scales, including small time scale. The weather should also take into account environmental issue on small time scale, airborne transport, water cycle, atmospheric chemistry, land change use, ecosystem, and finally go to impacts that include extreme weather events, climate-induced health impacts, toxic nuclear and disease transport, flooding, drought, water availability, air pollution, changes in habitat, loss of biodiversity, so that in addition to moderating influences, we can also adapt to what could happen in the future. And here, essentially, the research that is probably working around those model development needs to better connect with the people who are trying to respond to the problem and to adapt, have our society basically being ready to take what could become a major crisis for the planet in the decades ahead. So there is a mobilization of this community that is needed. It's happening through international programs like, for example, Future Earth or the World Climate Research Program, but many others too. And I hope that you will support this kind of approach that is interdisciplinary and also societally relevant. So thank you very much. Enhancing adaptive capacity for society in the context of changing weather and climate, that's what we want. So thank you very much. I'll be happy to respond to your questions.
Thank you very much, Guy. It was very interesting. I enjoyed it a lot. I hope our viewers enjoyed it a lot as well. So yeah, I want to thank you, and I also want to apologize because we had the first glitch of the week, maybe, with going live. So we were out of the live stream for 3 minutes, I was told, but we've been back for most of the second part of your talk. So we still had over 120 viewers, maybe more now, and we have only 3 minutes, I think, 2 or 3 minutes left. So I will ask you one question which we have received in the chat. I think it relates to the climate intervention point that you made earlier. And the question is about unknown or negative consequences. And the question is there any way to have trials to test the strategies that are in the pipeline for the future?
Well, it is very, very dangerous and difficult to really try to test those proposed solution for climate interventions. I think that the best way is to do it with models rather than doing it with real, I mean, putting a lot of particle in the atmosphere is very difficult. But we have ways by which we can learn things. For example, a big volcanic eruption is very, very similar to injecting particles in the atmosphere, because volcanic eruption launch a lot of particles in the atmosphere. And so we haven't had a big eruption for many years now. I think the last one was Pinatubo. And Pinatubo injected, I forgot exactly the number, but I think it's 20 megatons or something like that of particles, or I forget exactly the numbers, but it was substantial and probably very similar to what we would need to get the climate stabilized. We measured, of course, after Pinatubo, a reduction in the mean surface temperature. I mean, you see that in the data. So the system seems to work. But of course, the volcanic eruption happens once, and then it takes about 2 or 3 years for the particles to go away. Even after 1 year, the number of particles are already fading, or they are displaced towards the pole, for example. So if we had another volcanic eruption, I'm sure that this community would be really looking at the consequences. We have to be real careful also for political reasons. For example, I know that during the Cold War, the Americans, for example, were thinking of destroying the ozone over part of the Soviet Union at that time, which was another geoengineering activity. And it wasn't done because people realized that it would also hit not only the Russians, but the whole world, including the Americans who could do it. But potentially, it was a way to study how, for example, bromine released over the polar region could destroy ozone. So it seems to me that we have to think more about it, to study that, and perhaps to discover that there are regions of the world where launching particles in the atmosphere would lead to secondary effect. The only interesting technology that I think we need to pursue very, very strongly is carbon capturing. But nobody knows exactly how to do it. It's okay, perhaps, to capture some of the carbon from the atmosphere, but you have to store it and make sure it doesn't reappear in the atmosphere later on. So it is a scientific problem. It is also a political problem. You need certainly an international agreement to control this kind of perturbation at the global scale.
Thank you, Guy. I think I'm looking at my colleagues. Yeah, I think we don't have time for one more question. I wanted to, but I think we'll have to move on, unfortunately. So it's very interesting. I will send you a couple more questions that we can post answers in the chat later on to continue this. And I want to thank you again. It was really interesting and it was really good to have you. I'm glad we could have you today. Thanks a lot. And I hope you enjoyed it and that our viewers enjoyed it too.
And thank you very much again for the invitation.
That was a pleasure. Thank you very much.
If in the audience people have more questions, they can always email them to me.
Or send them to us and we will forward.
Yeah.
Thank you very much. Have a good day and see you soon. Goodbye.
Bye-bye.
Thank you, everyone.